In 2026, the primary financial strain for AI companies is no longer training the models. The real cash burn begins the moment a model goes live to serve thousands of queries at scale. For a long time, the technical barrier causing this financial drain was a rigid process called static batching. Static batching estimates the maximum possible answer length, blocking off massive chunks of GPU memory, regardless of actual need. Most of this rigidly bounded memory sits empty. The GPU inevitably runs out of capacity and crashes, despite being functionally idle. Teams ignoring this waste are forced to rent premium GPU clusters just to host empty space, destroying the application's unit economics before the product even launches. There's a common misconception that simply fitting a model into VRAM guarantees fast performance. VRAM determines fit, but it does not determine speed. You do not pick an inference engine first. You pick a hardware strategy, a workload shape, and a serving model. The engine follows. The engine itself is not the AI model. It operates as the traffic cop, the memory manager, and the scheduler. The software must perfectly match the physical realities of the memory hierarchy, the interconnects, and the operational maturity of the specific environment it runs in. Matching the engine directly to those physical constraints is the only proven way to turn raw computing capacity into a usable, cost-effective product. To understand these constraints, we have to divide the language model workload into two distinct phases, the compute-heavy prefill phase and the memory-heavy decode phase. The prefill phase reads the initial prompt and builds out the foundational memory cache. The decode phase generates the output one single token at a time. This process is strictly bound by memory bandwidth rather than peak compute power. This visualization shows the key value cache in action. As concurrent users and context links increase, these data blocks rapidly multiply and stack up against a fixed memory ceiling. Long context workloads will completely exhaust system memory due to this expanding cache, even if the model weights themselves fit perfectly on the card. Raw speed in AI inference is simply a math equation of efficient memory movement combined with rigorous scheduling. For offline environments, unusual hardware constraints, or single laptop prototypes, llama.cpp handles the job. On the Apple ecosystem, the MLX engine uses Apple Silicon's unique unified memory to fit massive quantized models that would normally require enterprise data center cards. On standard consumer and video graphics cards, engines like XLMA v2 and v3 maximize pure speed using low-bit weights. These local engines are highly capable for prototyping, but they lack the continuous batching and multi-tenant routing required to handle simultaneous users in a live environment. They prioritize extreme hardware flexibility and desktop control, explicitly sacrificing the ability to scale up to public-facing traffic. Moving to production serving, vLLM is the default standard. It utilizes a technique called page detention to eliminate memory fragmentation, allowing a single card to handle hundreds of simultaneous chats. Hugging faces, TGI, engine tackles extreme input lengths, using conversation caching to process 200,000 token documents highly efficiently. TG uniquely prevents vendor lock-in, allowing teams to seamlessly migrate workloads away from NVIDIA to alternative computing hardware. On the extreme end, TensorRT-LLM abandons general flexibility entirely, compiling models directly into hardware-specific graphs for maximum speed. This level of specialized performance is engineered exclusively for premium enterprise hardware environments. In the enterprise production tier, there are no perfect solutions. Every engine trades away a specific convenience to conquer a distinct physical bottleneck. This chart illustrates the ultimate reality check for AI deployment, a ruthless three-way trade-off between raw efficiency, ecosystem flexibility, and execution complexity. Maximizing speed completely drains the flexibility and complexity scores. You cannot maximize all three metrics at once. Deploying an engine like TensorRT requires highly specialized MLOps engineers. Their salaries often eclipse the entire monthly GPU computing bill. The decision map is strictly conditional. Use llama.cpp for laptops, MLX for Mac, vLLM for chat APIs, TGI for long documents, and TensorRT-LLM for massive data centers. An inference engine's actual value has nothing to do with vanity speed metrics. It is measured strictly by its alignment with your team's exact expertise, your actual traffic shape, and your hardware budget.